Kandice and partners Lauren, and in this video we're pretty much just going to be talking about projectile motion. Specifically, we're going to look at how angle of projectile takeoff, the initial velocity of the projectile, and drag force affect the horizontal displacement of a golf ball.
So just as Kandice said, we're going to first look at how the angle of takeoff affects the horizontal displacement of a golf ball. So a sand wedge is a very lofted club. The typical sand wedge is at 56 degrees. The typical golf swing is about 100 miles per hour, which corresponds to 44.7 meters per second. So we'll use that as our initial velocity. Down here we've created a picture, which is always helpful to draw. So we see the initial takeoff angle is 56 degrees, and then this is the path that the golf ball will take. And then we have our horizontal displacement at the bottom. So first off, it's always important to separate into the X and Y directions first. So you can see we've created another picture here depicting the initial velocity in the X and the initial velocity in the Y direction. So we use our trigonometry to find V initial X and V initial Y by just using sine and cosine laws. We're going to work in the Y direction first because it's much easier when we know the acceleration. So in the Y direction, the acceleration will always be gravity, so negative 9.8 meters per second. So our second step is using that knowledge to figure out what the total time is. So again, we're working just in the Y direction. We use V final equals V initial plus AT. We've put in all of our numbers, so V initial Y, negative 9.8 meters per second to find T. You can see here V final we've used as 0 because we're just using the first half of the trajectory because we actually don't know what the final velocity is of the full trajectory. So T equals 3.78 seconds for the first half. Now here we're obviously assuming that it's a perfect trajectory and it's perfectly symmetrical. So to find T total, we'll just multiply 3.78 times 2 to find 7.56 seconds for the total flight time. Now we can pop into the X direction, plug in our time that we found, use V initial X, and here we can find the horizontal displacement of 188.9 meters.
Great. Oh, hey.
Now we're going to compare that number that we just got to the 7-iron. So a 7-iron is 34 degrees loft. Again, we're going to use our V initial as 44.7 meters per second. So we're keeping that constant and just adjusting the angle of takeoff. So here we've drawn our picture again, 34 degrees. We're going to go through the exact same steps. So break it up into its components, work in the Y direction first. Again, take only the first half of the trajectory to find the time. So the time of the first half is 2.55 seconds. Multiply it by 2 for T total of 5.1 seconds. And now we can work in the X direction. So we use that same equation, plug in all our numbers, use V initial X, be sure to do that. And then we find that the distance is 227.97 meters. So it is much longer than what we found for the sand wedge, which was 188.9 meters.
Okay, so now what we're going to do is we're going to keep the club and therefore the angle consistent as well. And what we're going to vary is the initial velocity of the projectile and see how that affects the horizontal displacement of the golf ball. So as we just saw, as Lauren just demonstrated, when we used the 7-iron, which was an initial angle of 34 degrees, when the initial velocity was 100 miles per hour or 44.7 meters per second, the horizontal displacement of the ball was 227.97 meters. Now I want to see if we slow things down a little bit and the initial velocity is only 75 miles per hour or 33.5 meters per second, but the initial angle is still the same because we're using the 7-iron, and see what the horizontal displacement is now. So Lauren really went into a lot of the explanations, so I'm not going to get into that again, but you can see how again we broke down the initial velocity here into the Y and X components, finding an initial velocity in the Y direction of 18.75 meters per second and an initial velocity in the X direction of 27.79 meters per second. Again, plugging in the initial velocity in the y direction into this equation, and assuming that at maximum vertical displacement, the final velocity in the direction is 0, we end up finding that if we assume that the projectile motion is symmetric, total time spent in flight is 3.826 seconds. So again, we come up here and use that time to find the horizontal displacement, again assuming that acceleration in the x direction is 0, and we find that using initial velocity of 75 miles per hour, the displacement is much less than what it was using 100 miles per hour, right? It's about 106.32 meters compared to about 227.97.
So now we're going to talk about how drag force affects the horizontal displacement of the golf ball. Here we have two pictures. The top is depicting a golf ball with a smooth surface, so there's no dimples. The bottom is a golf ball with dimples, so you can see it's not a smooth surface. If our golf ball is traveling in this direction as we drew it before, the air is going to hit it going in this direction. So you can see as the air hits the golf ball, it's going to be pushed out on the edge of each side in three-dimensional space. So back here is what we call a turbulent layer. So here the air is all mixing from each side and it's creating turbulence, which really affects the pressure behind the golf ball versus the pressure in front. So this pressure differential is actually what matters most as far as how much drag affects the displacement of the golf ball. Down here, we see that the dimples create a turbulent boundary layer, which is actually this right here. That makes it so that as the air hits the golf ball, instead of going further back and having this large turbulent boundary layer, there's less turbulence. So you can see this area is much smaller than this area. That creates a less pressure differential as far as the front of the ball versus the back of the ball, which will allow the ball to go further. So it's all about the pressure differential. Less turbulence equals less pressure drag, which is really good reason why we have dimples on our golf ball. So the dimples actually allow it so that the golf ball can go a further horizontal distance.